All right, so we're going to finish off our chapter 12 today and then start chapter 13. So chapter 12 is just the leftovers of intro to metabolism, just looking at the introductory molecules that we need to have in order to do all of our thermodynamics. I do have the test to get back at the end of the class. Overall, pretty good, very good. I think the average is like an 85. It's pretty solid. So, let's see. Okay, so we left off looking at this guy over here is NAD+. I decided I'd draw him to make him a little bit bigger. Let's see. This camera's what I want. Oh, that's not bad. Okay, so this is NAD+. Bless you. So it's nicotinamide adenine dinucleotide. It undergoes the reaction. NAD plus 2 electrons plus 1 proton makes NADH. This 1 proton attaches here. And so when the proton attaches there, it no longer is NAD+. It loses that positive charge and just becomes NADH. Looking at why we call it nicotinamide adenine dinucleotide, this functionality right here, that's adenine. Anyone know what kind of sugar this is? Ribose is a ribose. Oop, I forgot my extra questions on this. All right, so an adenine attached to a ribose attached to 2 phosphate groups. All that together is ADP, which stands for which, as the name implies, is an adenine attached to 2 phosphates. This guy up here is the nicotinamide. Nicotinamide. And the dinucleotide comes from the fact that you have 2 bases attached to sugars. Right, so the dinucleotide means I could divide it up this way. Adenine attached to a sugar is a nucleotide, then nicotinamide attached to a sugar is a nucleotide. The adenine one is used in DNA, the nicotinamide is only used in this molecule. So, why we need this guy? Its job is to transport electrons. Specifically NAD plus and the NADH. It's used in the breakdown of products, especially in the citric acid cycle and glycolysis. That's where we're going to run into it the most. Its cousin is NADPH. Which is a phosphorylated NAD plus, so now it's NADP plus. And this phosphoryl group would be found here, so it would take off that alcohol and turn it to a PO3 functionality. I guess PO4 minus. And NADP plus and NADPH are used in biosynthesis. So they're found in 2 different cycles.
It says NAD plus and NADH is used in the breakdown of products. Is that of CAC and glycolysis? Or is that?
It's found in those cycles.
Okay.
Yep. All right, so last question before I leave this page. Is NAD plus an oxidizing agent or reducing agent based on the fact that it's accepting electrons? This is good review because we're going to do a lot of redox for the next few weeks. It is an oxidizing agent. Correct. So NAD plus is an oxidizing agent. What would that make NADH? It's a reducing agent. Mm-hmm. And the same thing can be said for NADP plus. It is an oxidizing agent. It's a reducing agent. Questions about NAD, NAD plus, P plus? Okay. Okay, so let's take a look at FAD and FADH2. I didn't finish my molecule. Let's see, I need this and that. Yeah. All right, so the mechanism of FAD is to accept 2 electrons and 2 protons to become FADH2. FAD stands for flavin. Flavin adenine dinucleotide. So the adenine is the same part of the molecule we had before. This is still adenine. This guy up here is a flavin. Then we have our same ribose, which makes this a dinucleotide, and this flavin functionality attached to that long chain. It's the reason the other part's called dinucleotide. Let's see what else. The two protons we have to accept in order to become FADH2 are attached to this nitrogen and this nitrogen. All right. So FAD is derived in the body from vitamin B2, which is riboflavin. So a good reason to eat your B2 vitamins so you have some FAD in your body. It's mostly used in the citric acid cycle for electron transport, just like we did. Yeah, question?
Sorry, the second phosphate that's attached to the sugar, is there an O and then it's crossed out?
No, it should be PO ring. So it should be OPOPO ring. It's the exact same molecule that's on your sheet. I just drew it bigger. So OPOPO to the ring. All right, so mostly used in the citric acid cycle is where we're going to see it. And the unique thing about this is that it can donate 1 or 2 electrons at a time. Because it can take in 2 electrons, and it can choose to release them either both at the same time or do 1 and then do the same. All right, so our last molecule, which I'll draw real quick, is coenzyme A. That mostly all fits on there. All right, so coenzyme I we're going to run into a few times. Oh, I forgot my conjugation. There we go. We're going to see it most often in the oxidation of pyruvate in the citric acid cycle. What's this functionality over here called, this SH guy? Starts with a T. Thiol. It is a thiol. Super important. Circle that if you don't remember. It is a thiol. Anybody recognize this portion right here from like the past two molecules? Adenine, ribose, 2 phosphates, that's ADP. So all 3 of these molecules have ADP in them. They all have an adenine, ribose, 2 phosphates, which is why they're all linked together, because they all have a similar energy source. The other version of CoA that we'll see is called acetyl-CoA. And acetyl-CoA converts that SH functional group to a C to an acetyl group. So this thiol group will then, actually, it'll be more like this. That S stays there, but loses the H and gets an acetyl group. So it changed, if it was acetyl-CoA, the H is no longer there. It would be S, C, double bond O, double bond to a methyl group. And we will use acetyl-CoA in the citric acid cycle and the electron transport chain. Okay, any questions about our 3 big molecules that we're going to run into a lot? They're not enzymes exactly, which is why we have to deal with them separately. Yeah, which way?
Just to the other side.
Here, I can move this too. I don't know if that's better. All right, in that case, just as a quick review of everywhere we're going to be in the next, 4 or 5 weeks. We have our 4 categories of biopolymers. We have our proteins, nucleic acids, polysaccharides, and trait acylglycerides. Those will be broken down through a variety of mechanisms to become our monomers: amino acids, nucleotides, monosaccharides, and fatty acids. These monomers can then enter a variety of different cycles and become 2 or 3 carbon intermediates, some of which just return to the monomeric form, some of which will enter our citric acid cycle. Depending on what organism we're talking about, we could hint up photosynthesis. We don't do photosynthesis in this semester. Biochem 2, that's photosynthesis. But citric acid cycle, which then enters into the oxidative phosphorylation system, which is where we run to our NADH. QH2, we'll talk about a little bit later. That's a really cool molecule. In the end, we make energy and water, and we have our original catalysts ready to enter back into the system. So, we're going to start working our way through the citric acid cycle. Oh, in a few minutes. Very excited. Before we get there, we got to talk about thermo. So, thermodynamics is the system that drives all of these reactions. The requirements for a reaction to proceed using free energy that the reactions need to be specific. What do we know about enzymes that helps us out with this? Enzymes are pretty specific. So, if we use enzymes, this is met. The second requirement is that the entire set of reactions needs to be thermodynamically favored. So thermo is a state function, right? It doesn't matter all the steps in the middle, it just matters how much energy you had when you started the reaction and how much you end up with at the end. And that difference tells you if it's thermodynamically favored or not. So for our reaction, let's say I have this imaginary reaction. I have some amount of A and some amount of B reacting to produce some amount of C and some amount of D. You could figure out the standard state of free energy, right? That's what the 0 means. If you were in Gen Chem, you could figure this out. So you remember what the standard state is? When I said you're at STP to do your reaction, it was 1 atmosphere, room temperature, right? Is your body at room temperature on the insides? No. The insides of your body are not all at 1 atmosphere either. So we cannot use the standard state free energy. We can, however, work around it. So this should look kind of familiar, vaguely familiar from the end of Chem 109. Where standard state free energy plus the gas constant plus temperature times the natural log of products over reactants, each raised to the stoichiometric coefficients, equals free energy, just regular free energy. Oh, because that's the other thing. Standard state is 1 atmosphere, room temperature, 1 molar, which not everything in your body is 1 molar. So we got to take into account temperature, pressure, concentration. So we definitely did this, you did this a lot in Chem 109, working it out. And then at equilibrium would have non-standard state delta G, so just regular free energy equals 0. Which if that is true, let's say we're at equilibrium. Yep, I lost the negative sign. There it is. Alex may be familiar. If you're at equilibrium, no, not familiar at all. You need to dust off some cobwebs. Where delta G equals negative RT ln big KEQ, which is the equilibrium constant for the reaction, because the equilibrium constant depends on concentration. Which we then rewrite as delta G 0 prime equals negative RT ln of KEQ. Where G prime, or G0 prime is the standard free energy of change for the reaction, which is specific for equilibrium at known concentrations. Which means all of our reactions are now temperature dependent, pressure dependent, and concentration dependent. Temperature and pressure we're not going to worry about so much. We're going to assume that your body's not doing anything crazy, you're not overheating, you're not under a vacuum. Concentration is going to be the one we're going to be most concerned about, the concentration dependency of all these reactions. Lucky for us, enzymes that catalyze these reactions that are always found near equilibrium have the following characteristics. They tend to act quickly, which means they have a high kcat. They have a high turnover number. Because they act quickly, they restore the equilibrium concentrations fast. And the overall net rate of these equilibrium reactions are regulated by the concentrations of substrates and products around them all the time. So we don't get too far off of equilibrium. So there's going to be reactions in our citric acid cycle that are always delta G negative, and there's others that are right at delta G 0. But because there's a lot of substrate, it should push it through to the next step. Okay, that's my 2-minute review on thermodynamics. The last molecule we're going to be concerned with is everybody's favorite molecule, ATP. Yay, ATP. All right, we have our old friend adenosine, which is that attached to the ribose. We got a MP, a DP, a TP, depending on how many phosphates are attached. Its job is to act as an energy conduit between high and low energy compounds. What that means is that it's able to work with coupled reactions. So if you have a non-spontaneous, right, a delta G greater than 0 reaction, you can couple that to a very exergonic reaction and then force those two reactions overall to have a delta G less than 0. And ATP is often the molecule that's used in that coupling to encourage the overall reaction to have a delta G less than 0. So it's special for several reasons, but 2 of them is that it drives thermodynamically unfavorable reactions through the cleavage of high energy bonds. These high energy bonds are the phosphoanhydride bonds that are listed up there. So the phosphoanhydride bonds are the high energy ones that when they're cleaved, they release a large amount of energy. And the question is, why do we have such a large energy release from the cleavage of what seems like a regular old bond? There are really 2 parts to this answer. Turns turns out that the ATP hydrolysis products are more stable than the ATP reactants. So when I have ATP, which I'll just shorthand like that. ATP has an overall charge at 3 minus. From what you know of chemistry in general, how happy are these oxygens to all have a full-on negative charge and be all lined up with each other? They're not happy, right? That's a lot of negative charge all on one side of the molecule. It's a lot of electrostatic repulsion because this side over here has 2 negative charges on opposing oxygens, and there's another 3 lined up along here. If you then convert to this, you've gotten rid of some of that unfavorableness that was existing. So you've gotten rid of the electrostatic repulsions, you've gotten rid of some of the steric hindrance. So this product is more stable than the reactant. So that's one reason that is a high energy bond.
There's still 2 negative oxygens together, though.
Mm-hmm. But there were all together like 4, and now we're down to 3. I'm not saying it's happy. I'm just saying it's better. Yeah. Its preference would be, which is part number 2. We'll do ATP. So ATP has these phosphoanhydride bonds. They have less resonance stabilization than an inorganic phosphate by itself. So if we look at, we'll look at the end. We'll look at ATP again. So I've drawn it where the double bond is to this oxygen, and these 2 are fully negative. And obviously the resonance structure for that, I could have drawn this double bond between any of those 3 oxygens, right? They're all equivalent. So really it's better to draw it instead of a double bond. It's more like something like this, where that double bond is shared, and that full-on negative charge is partial negative charge on all 3 of these. That would be more correct.
So you're just seeing partial.
Because the double bond is really shared between all 3, so no one oxygen is really fully negative. Double bonds in resonance amongst all those. But I can't do that as well for these middle ones, right? There's only one other oxygen it could be in resonance with. But regular old PI over here, inorganic phosphate, is really, that double bond is shared between all those oxygens. I guess, to be more correct, it should be like that. So it has more opportunity for resonance, which makes PI more stable. So phosphoanhydride bonds are high energy because the products are more stable. Both the adenosine product is more stable and the inorganic phosphate that releases are more stable. So it prefers to break apart. And when it breaks apart, releases a ridiculous amount of energy to go on and do other chemistry. Good. We have the last slide. The PowerPoint is just telling us where ATP will be found. But we're going to talk about ATP a lot, so we're going to consume it and regenerate it. So let's go ahead and take a look at the beginning of chapter, whatever's next, 12, 10, 12, 11? What chapter's next? 13. Half my notes are from one book, half from another book, and all the chapter numbers move around. There we go, 13. All right, so chapter 13, we'll start with just some very basic introduction to glycolysis. I don't know why it's so tiny. All right, so glycolysis, the overall point of glycolysis How many people have seen glycolysis in at least one other class? Most. Okay, good. Lucky for you, we're going to spend most of our time looking at the mechanisms. Because I don't want to just go over it because you guys have already seen it. So we're going to add in a layer of organic mechanisms. Good. All right, so the overall goal of glycolysis is to convert glucose. Oh. Bless you. So it's like a weight loss program. Convert glucose to pyruvate in 10 simple steps. You were a 6-membered molecule, will take you down to 3 in 10 simple steps. Through 9 intermediate steps. All right, so these metabolic pathways all have the following 3 things in common. I feel like I'm going super fast in this class, but I was just talking to my friend of mine who's in PA school, and she's like, you know what? Everything you covered in 2 semesters of biochem was review. Like they just had us read the book and show for the first aid and take a test, and moved on. I'm like, that is crazy. That's why I didn't go to PA school. Apparently, I don't learn that fast. Plus, I don't like dealing with cadavers. Or giving physical exams to other people, because that's the other thing, they're doing practice physical exams. Apparently, people volunteer to be the practice physical exam patients. I'm not exactly, I don't know why. I don't know. Maybe they're senior citizens who have nothing else to do. They have to act like they're sick in some kind of way. Yeah, they must get paid for that, right? So, yeah, maybe it's just like being dramatic. Maybe that's what it is. Yeah, so coming up in the next month, she is giving practice breast exams and prostate exams. So, again, if you know anyone who is looking to act, those practice exams are coming up next month. So, put flyers out, yeah. Not exactly sure who you'd get to sign up for that. All right, so each one of our steps will have a distinct enzyme to catalyze the reaction. There's going to be free energy consumed or released. Some have a net overall free energy change of 0. Some will need free energy and some will need to release free energy. Then the overall rate of the pathway, how quickly we start with glucose and end with pyruvate, will be controlled by enzymes for a variety of reasons, mostly dealing with inhibitors. That some are self-inhibited, some have other intermediates inhibit them, and then some are activated by energy released farther down the pathway. So there'll be different mechanisms the enzymes are allowed to go or stop. We'll do this last one for today. Some pathways are irreversible, which is pretty much a blanket statement. Some pathways, such as the highly, highly exergonic reactions, which means they release a lot of free energy. Those are going to be our irreversible ones. Right, because if it goes from here down to here, if you want to reverse that, then the energy to go back up is too much. Which means it confers a directionality on the reaction. Certain reactions will only proceed forward. They don't have the ability or the energy available to come back. And we'll need those on our pathway so that we definitely start heading towards our products. Our catabolic and anabolic products must differ. They have to go in 2 different directions. And we will separate them out by having different intermediates. You don't want to have your reaction that's building things up get crossed with something that's building things down. It's like in Ghostbusters, like I watched this weekend. If you cross the streams, everything blows up. So you can't have the streams crossed. They got to be one way or the other. That was my one Halloween movie I watched this weekend. That's as scary as I like it. The Stay Puft Marshmallow Man, that's about it. And finally, every metabolic pathway has a first committed step. As we'll see, starting Wednesday, most reactions in our pathway are at equilibrium. Their delta G is 0. But typically, there is an irreversible reaction early in the pathway. That forces the reaction one direction. So we will actually start with glycolysis. Talking about glucose on Wednesday.